Let us start this lecture with a thought process. True happiness cannot be gained by self gratification, rather by self annihilation. That was the thing what was followed in our country maybe 100 years back, but today with the market forces we are doing gratification. Okay. So let us now get back to what we learned in the last lecture. We basically looked at the reaction kinetics, right, and we also recall how to use the law of mass action, and in the end I talked about little bit how we will invoke the collision theory to evaluate the specific reaction rate. But what we will do today, we will now look at little way of how to represent this thing compactly, and then we will move at some kind of elementary reaction, then we will go back to the collision theory. Okay. So let us consider how a chemical reaction can be represented in a compact form, right. You might be wondering why I need to have that. This is the thing which was not very important maybe something 30-40 years back, right, to represent, to write the chemical reaction in a compact way. So let us see that we can do that in a very compact mathematical form into nu I mi, nu I dash, you keep in mind this is dash, summation over all the participating species I is equal to n, and this is of course the product side I is equal to 1 to n summation of all nu I double dash mi. So what is the meaning of that is we will explore little further, because if you look at it, looks to be little complex. So let us consider a chemical reaction, and for expressing it in terms of index notation. For example, if I say 3H going to the H2 plus H, that means in this case how many participating species are there? H and H2, that means 2. So if you look at this N, right, this N will be how many? It will be 2, right. So that will be N will be 2. Now I want to write in a very compact way. So if you look at it, is written in a very simple way 3H S2 plus H. But if I want to write in a more compact way, what I will have to do, like M1 is nothing but your H, right, because M1 and M2 there are total. If I look at this portion first I am looking at, right, like this is your reactant, this portion is reactant. So that means if I will consider this M1H, nu 1 dash will be definitely 3, and what will be nu 2 dash? 0, because there is nothing, no hydrogen here in the left hand side, in the reactant side, right. In the reactant side there is no hydrogen, right. So therefore because M2 is representing H2, and in the product side, like if you look at, this is hydrogen, 1 H atom on the product side, therefore nu 1 double dash is equal to 1, and 1 hydrogen molecule on the product side, therefore nu 2 double dash is equal to 1. Is that clear? Not getting? It looks to me. See what I am saying, I am just writing in a compact way. A question might be coming to mind, why we will do that? Okay, you think about why we want to do in a writing such a simple, very simple way I can write, right. Let us take another example, right, where you will tell me, like what is this N here? N is equal to capital N is equal to 3 HO2 HO2, right. Okay. So, now if I write down in this compact format, then what I will have to do? I will have to write in this way: M1 is equal to H, M2 is equal to O2 and M3 is HO2, right. Now, is it right whatever I nu 1 dash for H for the reactant, this is for reactant, right. This is the product side, right. Is it right or is it wrong? This is not right. Okay. So, what is that? Nu 2, if you look at O2, it is here O2. So, therefore, this will be wrong, this will be 1. Yes or no? Rest of the things is right. Are you getting? Yes or no? So, you know why we will write in such a complicated way? Because we want to, you know, simulate the kinetics. For that, computer won't understand this way. Computer understand in a compact mathematical form where you will be recognizing these spaces M1, M2, M3 like that, you know, it will be. Are you getting? So, for computer it is required, but earlier days it was not. Now, you will have to coding other things, and then of course, I will see whether I will get into, otherwise if want to, you will have to get into matrix format, you know, this will be easier to do that. That is why it is being done. I am just introducing, but it is not very important, right, so that you can really at least aware that yes, it can be written in this format. Now, above reactions are elementary reactions, right. So, it will be generally used for elementary reaction, because when you look at some kinetics, right, we always try to you know, use the elementary reaction, but that does not mean we will not be using global reaction, right, kinetics we will be using, but this is more predominant nowadays, particularly with the increase in computational power, people are going for better kinetics for simulation. So, now this is of course you are writing, but now you want to write reaction rate, you know, in a multi-step chemistry, and there are several reactions which are taking place. Let us take some example, right, which can be written in a very complex format, right, which we have already aware, that is reaction rate of ith species is summation of K. K is your specific reaction rate, right, isn't it? And C is the concentration of Mi, Mi is this all these spaces whatever represented, and nu I, right. Now, I will take 3 reactions. H2 is reacting with O2 going to HO2 and H. Keep in mind these are elementary reaction, there will be forward reaction KF1 and there will be backward reaction KR1, that is reverse reaction, right. Reaction rate, these are reaction rate, you know, coefficient or specific reaction rate, whatever you call, right. Similarly, HO2 KF2 OH plus O, and of course, there is a forward reaction, the you know reaction rate coefficient I have written, and KR2 is the reverse. Similarly, OH S2 going to the S2O and H. Now, I want to find out, right, what will be the reaction rate for H, let us say we will do that, right. How we are going to do? For any species I want to do for all these 3 reactions, because if you look at here the H is being produced, right. In this case H being also produced and also getting consumed. In the reaction 1 H is produced and also being consumed, you know, forward and reverse, okay. And similarly, in the reaction rate 3 H is being produced and also this thing, right. But if I consider hydrogen only in the reaction 1 and reaction 3, right, the reaction 2 hydrogen is not there, yes or no. Now, I want to write down, I will have to do in a systematic manner, right. So, for that net rate of production of an element, for example H or hydrogen, right, or species, rather I could have put it here species not element, okay. species is a better one. Species means it can be element, it can be molecule, it can be anything, okay. Species, right. Now, if I will write down, let us write down for CH as I have told this thing here, okay. So, what it would be dCH by dt, I can write down this is being produced. So, Kf1 CH2 CO2, yes or no, right. I will be talking about first is production, right, of H. So, then what I will do, I will get into the reaction 2, H being produced if you go in a reverse direction, otherwise no. So, then what will be that Kr2 COH CO, yes or no, yes or no, right. And here in this case the reaction 3, the H is produced in the forward direction. So, this will be Kf3 COH and CS2. This is about being produced and it is also getting destroyed. So, we will do in a systematic manner. Now, H is being destroyed, right. H is destroyed means how it is destroyed in the reverse direction. So, I will write down minus because destroyed, right, and Kr1 CHO2 and CH, yes or no, right. And similar way if you look at the destruction in this reaction 2, right, it is in the forward direction. So, I will write down Kf CH CO2 minus, so this is 2, right, and this is taking place in the reverse direction. So, this will be Kr3 CH2O CH, yes or no, right. So, just to make you familiarize, let me consider another this thing example, I mean how to write it down. This C S2 by dt will be, if you look at this H2 is being produced in the reverse way. So, therefore, what I will write down? I will write down Kr1 CHO2 CH, right, and in the reaction 2 hydrogen is not there. So, therefore, we will not consider, okay. And in this case in the reaction 3 the hydrogen is being produced in a reverse direction, right. So, I can write down Kr3 CH2O CH. Then I will have to look at destruction. See, destruction S2 in the forward direction. So, therefore, I can write down Kf1 CS2 CO2 and in the reaction 3 the S2 being destroyed in the forward direction. So, minus Kf3 C S2 COH, yes or no. So, now this reaction if you look at it will be if we use this compact scheme it can be written in a matrix format and the reaction rate you can substitute and then add together, all those things can be done very easily. I am not going to show that because it will be little complex and we will not be using in our this course, but whenever you are doing some kind of a programming and then simulating the things for simulation of the reacting flow, then you need to look at it. So, let us now get into the elementary reaction rates what we are considering. I will just dwell upon what I had also discussed. Let us consider 2 moles of hydrogen reacting with 1 mole of oxygen going to the product of 2 moles of water, right. And this is if you look at what is happening here, if you look in terms of breaking of bonds and forming of bonds in this case, right. how many bonds are being formed in broken? The reactant side, it is nothing but H, right, plus H, right, plus this is O double bond, right, minus O H plus O H, right. So, that means total in the reactant side 4 bonds are being broken, and in the product side total 4 bonds are being broken, which is 1 hydrogen molecule on the product side. Therefore, nu 2 double dash is equal to 1. 1 hydrogen molecule on the product side. Therefore, nu 2 double dash is equal to 1. Single step chemistry. Anyway, we do use single step chemistry, particularly in gas turbine application or IC engine, people do use for that, because that is very complex, right. We use a global reaction for modeling the flow, provided your computational capability is very, very small, and also you want to get answer quickly, right. But however, with the modern facilities, people are going for multi-step chemistry. Now, let us say that this kind of thing is really not occurring in nature. Are you getting my point? That means how this reaction will be taking place? Let us say, imagine that there is a certain chamber in which hydrogen oxygens are there, and you have raised certain temperature. Now, they will be, of course, even if you are not raising the temperature, they will be also colliding each other, right, because of randomness of the motion, and then it will move. But if when you increasing the temperature, what will happen? It will be basically colliding with a higher velocity or momentum. So, therefore, there will be some breaking of bond or forming of new bonds will be taking place. And if that is happening, now what is the likely to be happen, right, is that we will taking some 4 reactions to illustrate how what will be happening. As I told, this is known as also global reaction, right, and these global reactions won't occur in nature. It is only for our own convenience we have devised it, okay. But now, what will happen if hydrogen oxygen is colliding with each other, right? Imagine, then what will happen? It will go to HO2 plus H. In this case, what is happening? O2 is being broken, right? That means O2 is there, one bond is broken here, one bond, right, in the left hand side, right, okay. This is hydrogen is being broken, right, hydrogen is being broken, and then it is joined with O2 and became hydroperoxyl, right, hydroperoxy. HO2 is known as hydroperoxy, right, yes or no, hydroperoxy, right, and plus H. That means one bond is formed, which is likely to occur. You may say that why not H2 plus O2 can go to OH plus OH, is it likely to occur? As compared to this reaction, I can also have a reaction H2 plus O2 going to OH and OH, right, isn't it? Is it balanced? Okay. OH and OH is possible, but if you compare this reaction, if I can say 1A reaction, right, for just to segregate both the thing, right, that this is less likely to be formed. Why? Because it is in the reactant side 3 bonds are to be broken, and here 2 bonds are to be formed. So, therefore, it is less likely to occur as compared to reaction 1, but both are elementary. Are you getting? Both are elementary. Is that clear? Now, if it is there H, and if you look at H, what we call like H, O, these are radicals. And what is the meaning of radicals? Right? Radicals will be having unpair electron, that means they are ready to make a bond, right. Okay. See, for example, if you are having ego, right, you cannot have a friendship with other or a relationship with other, right. That means you are having ego, oh, I am great. So similarly, if there is a empty, or electrons are mobile, are there is a chance that there will be exchange and then taking. So therefore, this H and O are very reactive, and those are known as radicals. And this can be very important for making the reaction to happen, right. In chemical reaction, these are the things are very important. And then this H radical will be colliding with O2, because the O2 is a double bond, right. So it is not that easily to break. Keep in mind that in the first reaction, why not O2 will break? O2 will be a stronger bond, right, double bond. So therefore H is likely to break. Are you getting my point? Here, but H atom will be is a radical, so therefore it will be more energy that it can break. This will become OH and O. In this case, what is happening? That again the single bond is broken and then one bond is formed, right. So and then OH will be reacting with hydrogen, that is also possible, right. And then H2O will form and H, and H plus O2, this is the fourth reaction what I am trying to discuss. H plus O2 reacting with the M is a basically third body, right. This is M is third body. I have talked about that, let me again repeat this. When this third body, this is a trimolecular reactions, right. H plus O2 plus M going to the HO2 plus M, right. And this will be a inert body like nitrogen or maybe some other molecules which is not participating in this reaction particularly, that is known as third bodies, right. And this, if you look at, this is a very simple mechanism I want to illustrate and say that this is basically multi-step reaction mechanism. This is known as multi-step reaction mechanism. Do not think that I can use this as a substitute for the global reaction, that means hydrogen oxygen reacting in this this thing. It is not that. Nowadays people are using something minimum 20 reactions, right, to simulate the multi-step chemistry for hydrogen oxygen, okay, at this moment. But in earlier days people were happy with 2 steps, people were happy with 4 steps, right. But today because of computational power we could manage to use more number of steps, therefore the multi-step reaction mechanism. And whatever do, even if you do the 20 steps reaction mechanism, but still whether it is mimicking the nature or not, that is a $1 million question, okay. Are you getting? Are you getting? And in methane I had taken in 25 years back the something around 40 reaction steps for my PhD thesis, but today people are taking maybe 150 or 200 steps, right. And if you go for higher hydrocarbons, people are talking about 1000 multi-step reactions, or people are talking about 1200, 1500 like that. So coming back to that, let us consider the arbitrary molecular reactions AB, and we can find out reaction rate dCA by dt is equal to KCA. A is your coefficient, stoichiometric coefficient, and Cb, this is also B stoichiometric coefficient. So right, this we have seen. But now keep in mind that this K is the specific reaction rate or rate coefficient whose units is meter cube per kilomole second, and so K depends on temperature and activation energy, right. I have not discussed about that, but we will do little later on, not on the concentration, because this thing is valid for the elementary reaction as per the law of mass actions. And for finding out this K, right, we will have to invoke the collision theory, and for that what we will do, we will be looking at kinetic theory of gases, right, and which we will be discussing in the next lecture. Then I will have to go back to the collision theory and find out an expression for this specific reaction rate or the reaction rate coefficient, right. Thank you very much.